Hello students, in our last class we have discussed about the irreducible representation and great orthogonality theorem, and we have also observed the three types of cases in the great orthogonality theorem. And now I had said that from these three cases we develop mainly 5 rules, and which is very important to illustrate the irreducible representation in our character table. So in our today's class I will discuss about the 5 rules and how can we apply these 5 rules to form a character table. So first I'm coming to our rule number 1. What is that? The rule number 1, that is the number of irreducible representation, that is IR. For irreducible representation I am writing IR. So the number of irreducible representation of a group is equal to the number of classes in the group. So for example, if we take the C2V point group, in the C2V point group we can observe the symmetry operations like E, C2Z, sigma xz and sigma yz. So the total number of classes, that is 4, because 4 symmetry operations are there. So for the C2V point group, the order of the group is also 4, and the class of the group, that is also 4. Okay. So according to rule number 1, the number of irreducible representation for the C2V point group, which is also equal to the classes in the group, so that is equal to 4. So I have written here the C2V point group for your explanation. So in case of the C2V, I have written at the top, that is the 4 symmetry operations are there, that is E, C2Z, sigma xz and sigma yz. And at the left hand side you can see that I have written here the Bethe notation 1, Bethe notation 2, Bethe notation 3 and Bethe notation 4. As because the number of class, that is 4, so in case of the C2V point group, the number of irreducible representation, that is also 4, and in our character table we are writing the irreducible representation at the left hand side. Okay, so that is Bethe notation 1, Bethe notation 2, 3 and 4. So the left hand side, that is our irreducible representation, and at the top, that is our number of the symmetry elements, that is E, C2Z, sigma xz and sigma yz. Next I am coming to the rule number 2. In the rule number 2, that is the sum of the squares of the dimensions. The sum of the squares of the dimensions of the irreducible representation in a group is equal to the order of the group. I had already said in case of the C2V, the classes and the order, that is same. So the order of the C2V point group, that is also is equal to 4. So if I check the rule number 2, that is the sum of the squares of the dimensions of the irreducible representation, that is the order of the group. That means if I am writing the irreducible representation with respect to E and Bethe notation 1, that is K1, and in case of E, Bethe notation 2, L1, E and Bethe notation 3, that is M1, and E with respect to Bethe notation 4, that is N1. So I have written like that. And if you will check that the irreducible representation, I have written K1, K2, K3, K4 for Bethe notation 1, for Bethe notation 2, L1, L2, L3, L4, for Bethe notation 3, M1, M2, M3, M4, like that. So according to rule number 2, we can easily say that the K1 square plus L1 square plus M1 square plus N1 square, that should be equal to H. That is, the order is equal to the K1 square L1 square plus M1 square plus N1 square. Or you can take the other row also. So that is our K2 square plus L2 square plus M2 square plus N2 square, that is equal to H, means that is equal to 4. Or K3 square plus L3 square plus M3 square plus N3 square, that is equal to 4, like that. So that is our rule number 2. Next I have written rule number 3, that is the sum of the squares of the characters in any irreducible representation equal to the H. Okay, so the sum of the squares of the characters in any irreducible representation equal to H. So I had already said, for the irreducible representation, the characters, that is our, suppose I am taking the Bethe notation 1. So for this one, the character, that is K1, then again K2, then K3, then K4. So according to rule number 3, here we can write that K1 square plus K2 square plus K3 square plus K4 square, that is equal to H, that is 4. Or L1 square plus L2 square plus L3 square plus L4 square, that is equal to 4. Or M1 square plus M2 square plus M3 square plus M4 square, that is equal to 4, like that. Okay. So that is very easy. That is for the rule number 1. First of all, I have to write the irreducible representation, which is the number of the classes in the group. Then according to rule number 2, the K1 square plus L1 square plus M1 square plus N1 square, that is equal to order of the group. In case of C2V, that is 4. So like that. And from the rule number 3, we can say K1 square plus K2 square plus K3 square plus K4 square, that is equal to H, that is equal to 4. Or L1 square plus L2 square plus L3 square plus L4 square, that is equal to H or 4. So that is our rule 1, 2 and 3. Next, rule number 4. Rule number 4, that is the vectors whose components are the characters of two different irreducible representations are orthogonal. So the vectors whose components are the characters of two different irreducible representations are orthogonal. That means, suppose the vectors in case of E with respect to Bethe notation 1, that is K1. Again, if I will take another representation, that is Bethe notation 2, for E operation, that is L1. So like that, I can write from the rule number 4, that is K1 into L1 plus K2 into L2 plus K3 into L3 plus K4 into L4, and that should be is equal to 0, because that is our orthogonal. Okay, so I can take any other column also. That is, if I will write K1 into M1 plus K2 into M2 plus K3 into M3 plus K4 into M4, that should be is equal to 0 according to rule number 4. Or I can take other things also, that is L1 into M1 plus L2 into M2 plus L3 into M3 plus L4 into M4, that should be is equal to 1. So that is our rule number 4. So I have discussed here mainly rule 1, 2, 3 and 4, which is very, very important to represent the irreducible representation and to form the character table. Then I am going to rule number 5, that is the last rule which we are getting from the great orthogonality theorem. So in a given representation, that is reducible or irreducible, the characters of all matrices belonging to operations in the same class are identical. Okay, again, in a given representation, reducible or irreducible, the characters of all matrices belonging to operations in the same class are identical. So for this one, I can say that I have to write in the character table, that is, if the symmetry operation is 4, then for example C2V is E, C2Z, sigma xz and sigma yz, the number of irreducible representation should be 4. And if I want to write the reducible representation, which I have already discussed, that is for the C2V point group with respect to the 3n coordinate base, I can write that the reducible representation, that is 9, -1, 3, 1. So that you have to write also in your character table at the bottom part. Okay. So that is our 5 rules which we have derived from the great orthogonality theorem, which is very important. Next, I am just illustrating the 5 rules. So I have discussed these things also. Now I want to check the illustration of these 5 rules in practical level. Okay, in practical level. So the group C2V consisting of 4 elements and each in a separate class. Hence, there are 4 irreducible representation for this group. I have already said that with notation 1 to 4. So that is our rule number 1. And it is also required that the sum of the squares of the dimensions of this representation equal to h. So that is our rule number 2. So here I can say that according to our rule number 2, that is L1 square plus L2 square plus L3 square plus L4 square, that is equal to 4. So here I have written in different side, so that is the same thing. So that K1 square plus L1 square plus M1 square plus N1 square, that is equal to 4. So the only solution of these, what is the solution? That all these should be equal to 1. Okay, so if I will write that K1 square plus L1 square plus M1 square plus N1 square, that is equal to 4. That means K1 is equal to 1, L1 is equal to 1, M1 is equal to 1, and N1 is equal to also 1. So the group C2V has 4 one-dimensional irreducible representation. We had checked that. So suppose I am taking the I'm just checking for E operation, and we had already said that with respect to the E operations, the characters is known as the dimension. So if K1 is equal to L1 is equal to M1 is equal to N1, that is equal to 1, it means we have one-dimensional irreducible representation in case of the C2V point group. So I had written here, that is very, very important, that is our main character table for the C2V point group. So you can check the E portion. I had written here, that is the E portion, and the E portion with respect to Bethe notation 1 to 4, all the values are 1. Okay, all the values are 1. So that is mainly derived from the rule number 1 and 2, both. Next, now all other representation will have to such that chi means summation of I, chi I r square is equal to 4. That means which I had said in rule number 3, that is K1 square plus K2 square plus K3 square plus K4 square is equal to 1. Okay, so I had said that which can be true only if each chi I r is equal to plus minus 1. तो ये जो मैं यहाँ पर लिख रहा हूँ, ये जो Bethe notation 1, Bethe notation 2, Bethe notation 3, Bethe notation 4, ये with respect to that Bethe notations, if I will sum the elements, means if I will take the above one, that is 1 square plus 1 square plus 1 square plus 1 square, that is equal to 4, or 1 square plus 1 square minus 1 square plus minus 1 square, that should be equal to 4. So that means that should be plus minus 1. There is no other option. Moreover, in order for each of the other representations to be orthogonal to Bethe notation 1, that is our rule number 4. So there will have to be 2 plus 1 and 2 minus 1. So I can write that what we have to write at first when we form the character table. First we have to write the symmetry operations E with respect to the symmetry operation E. The Bethe notation 1 to 4, that should be is equal to 1. Okay, and there should be another column where the values of the Bethe notation are all equal. So you just check that at the top I have written for Bethe notation 1, all the values are 1. So the left hand side 1 1 1 1 and at the top 1 1 1 1. So that is fixed. And the other things which we have written here, that should be consist of plus minus 1. So that's why suppose I am writing for Bethe notation 2, that is 1 1 minus 1 minus 1. You can check if I will check our rule number 4, that is 1 into 1 plus 1 into 1 plus 1 into minus 1 plus 1 into minus 1, that is equal to 0. That should be is equal to 0. That should be the orthogonal. Okay. Or you can check Bethe notation 1 and 3, that is 1 into 1 plus 1 into minus 1 plus 1 into 1 plus 1 into minus 1, that also is equal to 4. So like that you have to write the irreducible representation. Okay. So first of all you have to write according to rule number 1 4 irreducible representation. Then according to rule number 2, all are 1 with respect to the E and all are 1 with respect to the Bethe notation 1. Then then from rule number 3 and rule number 4 we can check that the other values should be plus minus 1, and we have to write these values by maintaining our rule number 4, which is saying the orthogonal thing. Okay. So all of these representations are also orthogonal to one another. For example, I have written that Bethe notation 2 and Bethe notation 4 we have like that. So that is our C2V character table. That is not complete, but I have written the irreducible representation here in this way. Next, I am coming to our next example. Let us consider the group number C3V. I am coming to our next group, that is our C3V. So this consists of the following elements. What are these elements? That is E, 2C3 and 3 sigma V. We know that in case of the C3V, the 3 symmetry elements are there, that is E, C3 and sigma V, but C3 is 2 times and sigma V is also 3 times. So there are 3 irreducible representation, as because the number of class that is equal to 3, but here the order, what is the order? Order is here that E, 2C3 and 3 sigma V. So 1 plus 2 plus 3, that is 6. So the order is 6, but the class is 3. Okay. So when you write the character table, we can check at below we had written the incomplete character table. At the top we had written E, 2C3, 3 sigma V, and at the left hand side we had written Bethe notation 1 to 3, because the number of class that is 3, but the order is 6. Okay. So there are 3 irreducible representations. If we denote their dimensions by L1, L2 and L3, we have L1 square plus L2 square plus L3 square is equal to 8 is equal to 6. So that value should be 1, 1 and 2. Okay. So for this reason I had written here 1, 1 and 2 with respect to the E symmetry operation, 1, 1 and 2. So that we have written from our rule number 2. Then another thing is there, we have to write irreducible representation where all the values are 1. So at the top we have written 1, 1, 1, that is with respect to the Bethe notation 1. Next, here from rule number 3 we can write that 1 square plus 2 into 1 square plus 3 into 1 square, that is equal to 6. So if we check our Bethe notation 1, so for this case it satisfies our rule number 2 and our rule number 3. Next, now considering the rule number 4 by choosing Bethe notation 1 and Bethe notation 2. So if I will check our orthogonal thing with respect to our rule number 4, the other two values in Bethe notation 2 should be 1 and minus 1 because 1 into 1, 2 into 1 into 1 plus 3 into 1 into minus 1, that should be equal to 0. That's why I had written here for Bethe notation 2, 1 is fixed, the first with respect to the E, that is fixed, but with respect to 2C3 the value is 1, and with respect to 3 sigma V the value is minus 1. So that actually comes from our rule number 4, orthogonal rule. Okay. In case of the last one, that is in case of our irreducible representation 3, the values of character C3 and character sigma V can be find out by using orthogonality relationship. That means if I am checking here, so we can say that 1 into 2 plus 2 into 1 into chi 3 of C3 plus 3 into 1 into chi 3 of sigma V, that should be equal to 0 according to orthogonal rule. And with respect to the Bethe notation 2 and Bethe notation 3, we can write 1 into 2 plus 2 into 1 into chi 3 of C3 plus 3 into minus 1 into chi 3 into sigma V is equal to 0. So if we solve this one, then we can get that the chi 3 of sigma V is equal to 0 and chi 3 of C3 is equal to minus 1. So for this reason, I have written here chi 3 with respect to 2C3. Here I had written minus 1, and 3 sigma V and Bethe notation 3 I had written 0. Okay. So by applying rule 1 to 4 mainly, we can write our character table, mainly we can write our irreducible representation easily, which is the main heart of our character table. So for lastly, we can check by our rule number 3 that it is okay or not. If we take the Bethe notation 3 and the square of the sum, that should be equal to the order, so 2 square plus 2 into minus 1 square plus 3 into 0 square, that should be is equal to 6. Okay. So in this way, today mainly we have discussed about the 5 rules which we got from the great orthogonality theorem. That is rule 1 to rule 5. In the rule 1, mainly the number of irreducible representation we can check, that is which is the similar to the number of classes. And from rule number 2, we can say that if a particular symmetry operation, if I will write the elements of irreducible representation and I square these things and we sum up, then it will be equal to the number of the order of the group. And in case of rule number 3, we had checked also that for a particular irreducible representation for different symmetry operation, if I square these elements, it will be also equal to the number of the order of the group. And next, rule number 4, that is very important for orthogonality, which says that for different irreducible representation, but if I will apply the same symmetry operation and we multiply these values and ultimately we sum up, that means k1 into L1 plus k2 into L2 plus k3 into L3 plus k4 into L4, that should be equal to 0, or L1 plus M1 plus L2 into M2 plus L3 into M3 plus L4 into M4, that should be equal to 0. Then we have illustrated the 5 rules by using the C2V and C3V symmetry operations. So in case of C2V, by applying rule number 1 to 4, we had written the character table, that is incomplete character table, but this is the irreducible representations which we have to write in our C2V character table. So this is our character table. You can check. We have the symmetry operation EC2 sigma V prime or sigma xz and yz, and at the left 4 different types of the irreducible representation, and then we had written the values in 1 and minus 1. So in case of E, the 1 1 1 1, that is fixed, and in case of Bethe notation 1, these 1 1 1 1 also fixed, and the other values should be in 1 and minus 1. Then we had also applied these our rules in case of the C3V, in our C3V character table, mainly to determine the irreducible representation in our C3V point group. So in this case, it consists of the following elements, that is E, 2, C3 and 3 sigma V. So the class of this group, that is 3, but the order is 6. So Bethe notation 1, 2, 3 should be there. And by applying rule 1, rule 2 and rule 3, we had written here, this is our irreducible representations in case of the C3V point group. Okay, so in our next class I will discuss mainly what is the character table, and how can we correlate our reducible representation and irreducible representation. Okay, thank you.